Hello, myself and my group, consisting of Marwan McKemmer, Calvin Gilmore, Estelle Chan, and myself, Michael Viro, are here today to present our capstone project, the Mimic Me. With tens of thousands of injuries and hundreds of deaths from hazardous work environments each year in Canada, the goal of this device is to allow for workers who are otherwise exposed to these dangers by necessity of their profession to be able to work safely while maintaining efficiency and effectiveness. This also provides a benefit for employers, as it has the potential to reduce the number of liability and injury claims filed each year, while simultaneously protecting valuable skilled workers. While this may be the main objective of the design, it is far from the only plausible application, with applications in any gesture-based technology, such as controlling remote robotic vehicles, prosthesis, telesurgery, and many more. The Mimic Me is a robotic arm which is controlled through the analysis of surface electromyography signals taken from the operator's limb. These signals, taken from 4 places on the forearm and 1 location on the bicep, are processed using a machine learning algorithm in order to classify them as specific movements of the operator's limb. This classified data is then used to control motors of the robotic arm, which in this case is a simulation. This device works in real time with some small unavoidable delay in order to most accurately recreate the operator's intended movements. The first stage of our device is a signal preconditioning circuit. This consists of amplification and filtering stages in order to bring the surface EMG signals into usable ranges. These signals are then digitized using a microcontroller and processed using the machine learning algorithm after they are communicated to a computer. After classification, the resulting motor commands are sent to either the simulation or back through the microcontroller to hardware. The video that is about to be shown is demonstrating the real-time nature of our system. The movements being done are being classified through the electromyography readings and are communicated over Bluetooth to a second controller to be visually displayed in real time. As can be seen, there is effectively no delay in the classification of the movement. Here we see 5 movements being demonstrated: extension and flexion of the forearm, contraction of the bicep, making of a fist, and a rest position. This clip also shows the speed at which the system can operate and updates the output. The main limit on the system operating speed is the serial and Bluetooth communication. The next clip demonstrates the simulation of the end robotic arm. The classification of the EMG signal is used to drive the motion of the simulation in real time. Here we can see the motions being conducted by the system operator as well as the output of the simulation. There is a more significant time delay when compared to the previous videos. This is not a property of the system, but rather a limitation of the simulation software being used. The simulation has a slower cycle execution speed than the speed at which data can be sent to it. This causes delays to accumulate over time. It also requires another line of serial communication to work effectively as a simulation, again adding to the apparent delay. However, as most applications will be hardware-based and controlled directly from the secondary microcontroller, this will not require further serial communication. This extra delay should be significantly limited, if not entirely eliminated in practice. Thank you for your interest in our project. For further information, or if you have any questions, please feel free to stop by our booth on Expo Day.